Dear students, welcome back. In this lecture, we are going to continue the method of power series. In the previous lecture, we had introduced the method of power series for regular points, ordinary points, right? And we also introduced the notion of singular point and so on. So in this lecture, we are going to look at some special class of singular points for which you can apply the power series technique, which is called the Frobenius method. So this lecture I'm going to combine two lectures in order to avoid breaking the lecture into two parts. So more or less what we cover today is a content for two lectures, that is lecture 33 and lecture 44. Lecture 34. So basically the lecture of 25th June, which is Friday, and then the lecture of 28th June, which is the coming Monday. Okay, so let's start with lecture 33. So in the previous lecture, we had introduced the power series technique for an ordinary point. And those results that we obtained there cannot be extended to singular points. However, if your singular point behaves better, then you can apply some tweak of the power series method. Now, what is this better behaved singular point? It is the regular singular point. Okay. So, what is a regular singular point? So, if x naught is a singular point of the given ODE, and if x naught is such that x minus x naught px and x minus x naught square qx are both analytic. See, remember when we say x naught is a singular point of this ODE, which means that both p and q at x naught is not analytic, right? That's what this means when you say x naught is a singular point. So if it's a singular point and p and q are not analytic, but x minus x naught p and x minus x naught square of q both are analytic at x naught, then you say x naught is a regular singular point. So it's a singular point, but if you multiply with p x minus x naught and with q x minus x naught square, then you have that both these functions are analytic at x naught. If that happens, then your x naught is a regular singular point. Okay, let's look at some examples to understand. So take this ODE. So in this case, if you notice, your coefficient p is minus x by 2x square, which is minus 1 over 2x. So x equal to 0 or x naught equal to 0 is a singular point, right? Similarly, q of x is equal to x minus 5 over 2x square. Okay, now this again, x naught equal to 0 is a singular point for q as well, right? So both these are singular point, whereas let's see whether it's a regular singular point or not. So for regular singular point, what you should do, what is your p? P is x minus 2x square. This is your p. This should be multiplied by x minus 0, which is x, right? Because 0 is a singular point, so x minus x naught, which is x minus 0. So this, if you multiply, what you get is minus x square by 2x square, which gives you minus 1 over 2, and this is analytic. So x px is minus half is analytic. Similarly, x minus 5 2x squared, this is your q. If you multiply with this, x minus 0 whole square, which is x square, right? So x minus 5 x square 2x square gives you x minus 5 over x minus 5 over 2, which is analytic. So that's analytic. So this x naught equal to 0. So the 0, which is a singular point, is actually a regular singular point, because when you make this operation, those functions are analytic at x naught equal to 0. Okay. Okay. Now consider this ODE. Now in this ODE, what are the singular points? So what is your P? Your P is 2x minus 2 over x square minus 2 whole square, which is 2x square x minus 2. So in this case, x equal to 0 and x equal to 2 both are singular points for P. Similarly for Q, let's compute what is Q. Q is x plus 1 x square x minus 2 square. Okay, so here again you have x naught equal to 0 and x naught equal to 2, both are singular points, okay, for this P and Q. So if we need to verify whether they are regular singular points or not, you need to, with P you need to, so let's check whether x naught equal to 0, I mean the first one, whether x naught equal to 0 is a regular singular point or not. So which means you multiply by x here, you multiply by x squared here. If you do that, you multiply by x squared here, this goes off, and you multiply by x here, so multiply by x here, you get this, so 2x. So in this case, if you see x equal to 0 is fine here, that is for Q it is analytic at x equal to 0, whereas xp is not analytic, right, which means 0 is not a, so xpx is not analytic at x equal to 0, because we got 2x over 2, right, we got this x 2 over x into x minus 2, whereas for x square you got this, which is analytic. So one is not analytic, one is analytic, which means that x naught is not a regular point. It's it's not a regular singular point. Now let's take x naught equal to 2. In that case, you do what you compute is x minus 2 of P, and you compute x minus 2 square of Q. See what happens, right? So in this case, if you actually notice that x minus 2p, you get 2x square, which is analytic at x naught equal to 2, and here again this is also analytic at x naught equal to 2. So both are analytic, which means x naught equal to 2 is a regular singular point. Okay, so now you have understood what is a regular singular point. Okay, so now we have the result which talks about how to compute the solution using the power series method when at a point which is regular singular point. We have already seen how to use the method of power series when your x naught is an ordinary point, right? So when it's an ordinary point, both P and Q has to be analytic, and then right, P and Q has to be analytic at the ordinary point x naught, and then you use the power series form of y, substitute, equate like powers, you find the coefficients, and then that is how you compute the power series solutions of a second order ODE. Now if your point is a regular singular point, which means what? Both P and Q are not analytic at x naught. However, x minus x naught P and x minus x naught Q, right, both are analytic at x naught. So if that happens, then this ODE admits at least one. So there is at least one non-trivial solution of this form. Okay? Of this form, where this R that you have here in the power can be a real or complex number, may be determined, and the power series converges in some interval containing x naught, but except at x naught. So the radius of convergence is a punctured disk. So you have x naught, you have some interval around x naught, and you remove this point x naught, and in the rest of the place the series converges. Okay, so we are not going to prove this theorem. We are going to, of course, see it via examples, as always, as we have been doing throughout this course. But like always, I would like to give you the idea or motivation of how, why this, how did someone even come up with this kind of a form and so on, right? So, but that's kind of quite easy. You see, if you know x naught is a singular point, if you know that, then you know which means that both P and Q at x are not analytic about x naught. Whereas because it's a regular singular point, you know that x minus x naught P and x minus x naught square Q both are analytic, which means that you actually have x minus x naught P as some form of some series, right? About x naught, right? Because it's analytic, right? That's the assumption of regular, that's the definition of regular singular point. Regular singular point means that x minus x naught P is analytic, which means it has this form. Similarly, you have a similar relation for x minus x naught square Q, which also has some such, say, bk x minus x naught power k, some such form, right? So right? So what this means is that Q also has a series form, but it has negative powers of x minus x naught, because I can divide both sides by x minus x naught square, right? Same here, I can divide by x minus x naught, which means okay, let me erase some of this. Which means P has some form which actually starts with minus infinity, infinity, ak, x minus naught xk, where some of these ak's for negative case is non-zero for k negative, right? K negative integer, right? That's what this means, right? Here, if you divide here. Same here, when you say x minus x naught square is this, if you divide, then you have an expression for q also of similar form, where the coefficients corresponding to the negative index here are non-zero, right? That has to happen, and that is what gives you this motivation that here you have this x minus x naught power r, and this r can be determined. Okay, that's the idea behind this proof for regular singular point. So the fact that P and Q is not analytic because it's not a ordinary point, it's a singular point, but because it's a regular singular point, P and Q has an expansion which involves negative powers, and that is how you obtain a solution of the power series form. Okay, so that's the idea behind the proof. We will not go behind the proof. Let's just do this theorem and see this theorem via examples. Okay, so let's take an ODE. So this is the ODE that is given to us. Right? So in this case, what is P? P is minus x over, this is something which the example that we already saw in the previous slide. It's the same example, x minus 5 2x squared. This is P, and we have already seen in the previous example that x not equal to 0 is a singular point, but it's a regular singular point. Okay, so now we look for a solution via, so this method is called the Frobenius method, whatever this statement. So we now look for a solution of this form, power series form, where you have starting with some r. So this r is also to be determined. Okay, and such that C naught is not equal to 0. What is C naught? Basically the coefficient corresponding to x power r, right? C naught is the coefficient corresponding to x power r, and that cannot be 0, right? Because if that is 0, then basically what we are saying is that you have all positive powers, right? So what we are saying is that this so the coefficient of x power r cannot be cannot be 0. Okay, so you start with such a power series expansion. Okay, and then use that information in the ODE here. So in the previous method for ordinary point, we did not have r, we had r to be 0. Okay, but here because of the regular singular point situation, you have this additional r which is to be determined. Okay, so use this form of y in the ODE and substitute and equate power. So for that you need to differentiate y once, differentiate y twice, and so on. So if you differentiate y once, you get this. If you differentiate twice, you get this. So you have this series form. Now you plug it in this ODE here. Okay, then you get this. Okay, so here if you see this first term here is coming from here, right? This first term here is coming from this 2x square y double prime. Okay, and this k plus r, this term is coming from y prime, this x y prime. This term gives you this term, whereas this 5, this term is coming from this 5y. Okay, and this term here, last term, is coming from xy. Okay, so if you plug it in, so the ODE becomes this. Okay, so here again you have to equate. If you just accumulate all the like powers here and so on, you can write it as something power x power r and everything else of x power k plus r. Okay, and now if you equate coefficients, you have a relation, right? So if you equate coefficients, what you get is this is equal to 0, because right, this entire thing is equal to 0, but since C we have already assumed cannot be 0, so this has to be 0. This is called the indicial equation. Okay, so the equation that is going to give us the value of r. Okay, so indicial equation is the one that gives you the value of r, that is one, and then you have equating these, you have the recursive relation in terms of, the recursive relation of all the coefficients ck's. Okay, so you have the recursive relation ck. Fine. Okay, so if you solve for r in this quadratic equation here, you get two roots for r. So you get r1 equal to 2.5 and r2 is -1. Okay, these are the two values that you get for r. Now you use each of these r, because there is a value of r in this recursive relation. So right, so use each of these r separately, then you get two different solutions. Okay, that's the idea. So when you take r1 equal to 5/2 in the recursive relation, then you get this relation, okay, which is now independent of r. So ck is depending on ck -1. So if you use that information, you have all the coefficients, and then once you have all the coefficients, you plug it back in the relation that you started with, this one, right? Here you have all ck, so if you use that, you have the one series solution corresponding to r1 equal r1 corresponding to r1, which is 2.5. Okay, so now this is your one solution. Now for the second r2, second r, which is -1, the r2, the recursive relation will become something like this. So I'm not doing the calculation, you just have to do it, right? You just have to plug in -1, -1, -1 here and see what happens. So k -1, here it becomes k -2, here it becomes k -1, and so on. So if you simplify them, you are going to get this relation. Okay, so you have the relation here. So here even in the earlier case, you see you already have a C0 which is non-zero, right? And you have C1 which is given in terms of C0. So C1 is in terms of C0. C2 is in terms of C1, which is in terms of C0. So every constant every constant in the series can be written in terms of C0, which is why you have a C0 here. Similarly, here as well, you will see that all the constants can be written in terms of C0. So you will have a relation like this, C0. Right? Now if you see, you already have one solution here, y1, and right, corresponding to the r1. You have another solution here corresponding to r2, and it so happens that both these are linearly independent. You can just see that they are not constant multiple of each other. They are linearly independent. So the general solution is a linear combination of y1 and y2. This is the Frobenius series method, right? Frobenius method to find solutions for an ODE where about a regular singular point. Okay, is that okay? Okay, so now the situation that we are going to see is we have seen R1, R2, whatever we see, so whatever we saw in the previous example here, like we had two values for R2 and it was a quadratic equation in R because we started with a second order ODE, right? So you had the indicial equation which is a second order which is a quadratic equation. So you get two values for R, and each value of R gave you linearly independent solution, but that is not always the case. Okay, so that can change depending on situation, depending on ODEs. So whatever we have done here, so this example that I showed you here is an example just to illustrate the Frobenius method, but it is not always necessary that the two values of R, that is R1 and R2, will always give you two linearly independent solutions. That's not always the case. So we are going to look at the situation when it's possible, where it's possible to find all the solution, and if not, and then how are these solutions related to the R1 and R2 that you solve from the indicial equation. Okay. So the linear independence of solutions and its relation to R. So if you have a x0 which is a regular singular point, and if you have R1 and R2 which are the roots of the indicial equation, then you see this is a quadratic equation. So in general the solutions, so in general the roots of the quadratic equation are complex numbers. So R1 and R2 can be complex numbers. So you arrange R1 and R2 in such a way that the real part of R1 is always bigger than the real part of R2. Okay. So if you arrange it like that, right, then first situation, if you look at R1 minus R2, okay, and if that is a positive real number which is not 0 and which is not an integer. Okay, so when I say z plus here, what I mean, plus indicates that it's on the positive real line, z indicates the integer, so positive integer. When I say z plus, I am actually all positive integer, that means 0 is not included. So what we mean here is R1 minus R2 is not equal to 0 and is not equal to an integer. Okay, and right, so I am here. So in this result, we are ignoring the case. Suppose say R1 and R2 are complex numbers, then which means that and since they are roots of the quadratic equation, they appear as conjugate. So R1 minus R2 should be a purely imaginary number. If both are purely complex number, then they both are purely imaginary number. We are not dealing with that situation, and that is also can be handled, so let's not worry about that. So here we are only looking at the situations where R1 minus R2 is a real number such that it is not 0 and it is not integer. What happens then? What happens is that then you get two non-trivial linearly independent solution where y1 is x minus x0 power r1, right, and the series, and y2 is x minus x0 power r2, like the situation that we saw in the previous example. So in the previous example we had 2 r1 and r2, and corresponding to r1 and r2 we got linearly independent solution. That will happen, and the reason it happened is because if you check here, when you found the r1 and r2, where did you solve r1 and r2? Yeah, here. So you see r1 minus r2 is 5 by 2 minus r2, which is minus 1. So 5 by 2 plus 1. Okay, which is 7 by 2, 3.5, right? 2.5 plus 1, 3.5, and that's not equal to 0, and that's not equal to an integer, right? So in this case, which is why we had corresponding to each R1 you had one solution and they were linearly independent. Okay, and that's what the theorem is telling you, that if you have R1 minus R2 which is non-zero and not integer, then each R1 will give you a solution and both these solutions are linearly independent. Okay, that's situation 1. Situation 2, if R1 minus R2 is a positive integer, okay, it's a positive integer now, then the bigger integer, so the solution corresponding to the bigger root, which is R1, will give you one solution that will always exist. the other solution may and may not exist, but you can compute the other solution y2 as corresponding to R2 plus C times y1 log x minus x naught. So in this case, C can be 0. So if this capital C is 0, then you are in the situation like before, I mean the first case where you are distinct R1, R2. That can happen. Okay. So you understand what I am saying? In the previous case, we said this will give you two linearly independent solutions. That doesn't mean that if you have two linearly independent solutions, then this R1 and R2 satisfy this condition. Okay. So what we are saying here is that for R1 minus R2 with positive integer also, you can have a situation in general, I mean you can have a situation where the R1 and R2 will give you linearly, so the R1 and R2 will give you a linearly independent solutions, but in general it may not be linearly independent, and in that case you have an additional term like this. Okay, and the only condition here is that in both these cases, like in this case Cik, Ci0, that is when k equal to 0, the first the first coefficient is non-zero. Similarly here also the first coefficient is non-zero, the first coefficient is that's what we are saying here, right? Basically what we are saying is that whatever we had before, right? So the coefficient corresponding to x power r should be non-zero, right? Okay. So this is the second situation where you have R1 minus R2. So the difference is a positive integer. In that case, you have one solution. The other solution may be of this form. If not, if this is not linearly independent, then you have it in this form. The third situation is when R1 minus R2 is 0. Right? In that case as well, the R1, because R1 and R2 are same, so whether it's R1 and R2, will give you one solution like this where C10 is non-zero, the coefficient is non-zero, and the other solution has to be found. I mean the other solution which should be a linearly independent solution can be written like this, where it's R1 plus 1 and y1 times log x minus x naught. So the takeaway from this theorem is this, that you always have one solution which is of this form, okay, which is of this form, which is corresponding to the biggest or the largest R1. So corresponding to the largest R1, you always have a solution of this form. The second solution, because the second order equation, you need one more solution to find all the solutions, right? One more linearly independent solution, and that one more linearly independent solution may not always be possible to, it's not always easy to find that other linearly independent solution. So in this case you have linearly independent solution. In the other cases you have to do an extra effort to find that linearly independent solution. So something like the reduction order technique which we have used before, where we have said that if you know one solution, you can always find a linearly independent solution corresponding to that, right? Something like that can be employed here, because one solution you will find, so here corresponding to R1, the largest R, and the other solution can be found by the reduction order technique, right? So that's what the summary of this theorem is. Okay, so let's observe this theorem or understand this theorem via examples. We will see all the three cases in various situations. Okay, so let's take the first case. Okay, first example. So you take this ODE here. In this ODE, x0 is a regular singular point. So we are looking for a solution of this form where C0 is non-zero. Okay, so you differentiate this y and use it in this, substitute in this ODE and equate powers, right? So you differentiate, so this is your y prime, this is your y double prime, substitute in the ODE, if you equate, you get this equation here, whatever you have here. So if you equate powers, you are going to equate, since C naught is non-zero, you are going to get this is 0, which is a quadratic equation in R, which is the indicial equation that we have. Okay. So if you equate, so this equation that we had here is precisely this, which is 0, and then the remaining equation, this is going to give you this recursive relation for k bigger than or equal to 2, because k is equal to 2, right? So for k bigger than or equal to 2, you have this recursive relation. Okay, and you also have this equation. This is also equal to 0. Okay. Okay. So now, if you solve the indicial equation, you get the root R1 is 3 by 2 and R2 is minus 1. So R1 minus R2 is 2.5 again, which is a real number, which is not an integer, which is not a positive integer, and it's also not 0. So according to the theorem, you should have two linearly independent solutions corresponding to the distinct R here. Okay, so let's obtain that. So you have R1 and R2. So use the R1 first. R1 is 3 by 2. Use this R1 in the recursive relation. So you get this recursive relation here, right? So in this recursive relation, you have R. Use the first R1. So you get this recursive relation, and you get this solution. And if you substitute, find the coefficient, you see. So if you want, this is for k equal to 2, right? So for C2, it depends on C0, right? Similarly, every even index, so for all even k, they all depend on C0, right? And for all odd, if you use the R here, you can solve for C1 here, right? You will actually see that C1 will become 0. So what you will be left with is Y1, which is just this. Okay, which is just this. So, which is Y1. Now what is the solution corresponding to R2, which is minus 1? So wherever you had R, you plug in minus 1. Then again you will have a recursive relation. This is again all even indices depend on C0. So you will have a C0 relation, and all the odd indices should be 0 from the relation that you from the second relation, right? From this relation you will obtain C1, and you will see that that's 0. Okay, so you have a second solution, and this are linearly independent solution because they can't be obtained by any scalar multiple. So the general solution is a linear combination of these two. Okay, so that's the general solution. So this is the first case that we described, where the difference is a real number which is not 0 and not positive integer. You get two linearly independent solutions. Okay, fine. Now let's do another example which will illustrate the second situation. So you have an ODE here. So you have a P, Q, and you can observe from here that 0 is a singular point, and in fact it will be a regular singular point. Okay, so we are looking for a solution of this form where C0 is not equal to 0. Differentiate this Y, use it in this ODE, you will get an equation of this form. And equating, since C0 cannot be 0, equating the first term to 0, you get the indicial equation. The other terms will give you a recursive relation. This will give you a relation for C1. Okay, so if you solve for the indicial equation, so you get an indicial equation which is this. and then a recursive relation, which is this for k greater than or equal to 2, because this k is greater than or equal to because k is starting from 2 here. So now if you solve for this quadratic equation here, you get two roots, which is 5 by 2 and minus 1 by 2. Okay, and what is r1 minus r2? This is 2.5. 2.5 plus half, which is 3, which is a positive integer. So in this case, what is the theorem saying? That you can get so corresponding to the bigger r, which is in this case 5 by 2, corresponding to that you will get the Frobenius form solution, right? And then the other solution is a linearly independent solution which needs to be obtained from some other means. So let's see how we do it here. So let's plug in R1. So once you use R1, you will see that C1 is 0, because from this relation you have C1 from here. So use R1 value, equate this to 0, you will see that C1 is 0, because this product is equal to 0. This you will see is non-zero, so then C1 has to be 0. So C1 will be 0 and the recursive relation will give you this. And here you see, since C1 is 0, all the even indexed coefficients are all 0. All the odd indexed coefficients are all 0, and all the even index now depend on C0. So you have a relation for Y1. Now what about R2? In general, the theorem tells you cannot find R2. So let's just start with R2 and see what happens. Okay, so if you start with R2, plug R2 in the same relations that we had before, like earlier case, we will get C1 equal to 0, and then you have the recursive relation k for k like this. But here you see it's k minus 3, so you cannot do this for k equal to 3. So what happens in that case? What should you do for k equal to 3? Is that for k equal to 3, you write the relation as k, don't divide it, ck. This is the recursive relation for k equal to 3, and for other case you have it in this form, right? So since your C1 is 0, you can see that all the odd indexed coefficients here has to be 0 and so on. But here you see already when I put k equal to 3, you already see that this is 0 and this is C3. So 0 times C3 is C1, right? But C1 is already computed to be 0, which means this is 0, which means the choice of C3 is arbitrary, because for any choice of, C3 could be anything, right? Because this relation is always satisfied. So for k equal to 3, that's whatever I described, 3 into C3 is C1, making the choice of C3 generic, right? So for any C3 that you choose, this relation is always valid. So corresponding to this r equal to minus 1 more 2, now that you have found everything, so if you use these coefficients here, you are going to get y2, y2 to be this equation, right? So you have a linear combination of C0 and C3, right? Because you see, as I already explained here, there is already a C0, and all C0 will give you all the even index C. So all even index C are depending on C0, whereas because of this relation and C3 is arbitrary, all odd indexed C coefficients are all depending on C3. So you have this relation. So then you will have y2 to be this form. Now you see here the second term, this term here. If I bring this x cube outside, this becomes x cubed minus half, which is x 5 by 2, right? And whatever is left here is 1 plus, if you simplify them, you will see that this, whatever I have circled here, this equation is precisely the y1 that you obtained earlier, corresponding to 5 by 2. Right? So what I am saying here is that if you choose say C0 as 0 here and C3 as the original C3 here, sorry, C3, I mean this C0 here, then this y2 is nothing but the y1 solution. For that case, when you choose CZ, when you choose this is to be 0 and this is to be, say, some that old C0, then y2 is C1. So this solution y2 involves already the y1 solution. So more or less, this is a linear combination of two linearly independent solutions. So this y2, so this y2 is the general solution of the ODE. Okay, so you see, in this case, the R2 was directly giving you a general solution, right? The R1 gave you one solution, whereas R2 gave you a general solution for the second order ODE, because it involves two arbitrary constants C0, C3, right? This is one situation. Okay, now let's so as in the above example, when you had R1 minus R2 belonging to positive integer, it is possible to obtain general solution from the smaller root R2, right? So the theorem, we said it has to be something plus C times y1 log of something, right? So in this case, the capital C that you had in the theorem is 0, and you have a general solution coming out from R2. Okay, this is one situation. Let's look at another example, and this is again, we will illustrate the second situation where the difference is a positive integer, but then something else will happen. So you have an ODE, you can verify that x0 0 is a regular singular point. Okay, so use this Frobenius, I mean this power series form here, right, and substitute in the ODE. Okay, C0 is not equal to 0. Then if you equate, if you substitute and segregate terms appropriately, then you will get an equation of this form. Okay, so you get 0 equal to this form. Okay, now if you equate the like powers, then you already have, since C0 is not 0, you already have an indicial equation coming from here, and then the other one will give you the recursive relation. So you have the indicial equation here and the recursive relation here for k bigger than or equal to 1. So if you solve the quadratic equation in R, then you get two powers, which is two roots, which is 3 and 1, and their difference is a positive integer, which is 2. Okay, so now the bigger root is 3, so corresponding to the 3, if you substitute them in the relationship, then you can, then your recursive relation becomes this. Then if you plug it back, use the coefficients, then you actually see that y1 is C0 times x cube e power minus x. Okay, so the series can be actually written as x power minus x, e power minus x. Okay, so that's one solution that you obtained. Now what is the other linearly independent solution that you need to obtain? So the other solution is R2 equal to 1. Use that in the recursive relation. Here you will get a recursive relation of this form, but here again you see k not equal to 2 is not allowed. So for k equal to 2 situation, you think of the recursive relation as k minus 2 ck minus 1. This is how you imagine. So what happens in the case of k equal to 2? 0 times C2 plus C1 equal to 0 is what you will get from this relation. So okay, that's the relation that you will get, which tells you that C1 has to be 0 and C2 can be arbitrary. Okay, so in the first so when you get R2 equal to 1, so the first relation gives you C1 is equal to 0, right? From here, let's see. So from here you have R1. Okay, so you see, okay, yeah. So when you want to compute C1, so C1 is minus C0 by minus C1, so minus 1, which is C0. So C1 equal to C0 is coming from this relation first, and then k equal to 2 will give you this, which implies that C1 is 0, right? This, because this is 0 and the sum is 0, means C1 is 0, and if C1 is 0, so the first relation tells you that C1 is equal to C0, which means C0 is 0, but C0 we assume to be non-zero. That's the assumption that we start with, right? Because that is the coefficient of x power r. C0 is non-zero. So C0 is non-zero is a contradiction. So right? So C0 equal to 0 cannot happen, which means that corresponding to R2 equal to 1, there is no corresponding solution. Right? So in the previous example, we were able to get a general solution corresponding to the second root R2, which is the smaller root. In this case, the smaller root is not giving you any solution. Okay. So what do you do? You can ignore those, because the issue was because you had considered the this k equal to 2 as a recursive relation. If you ignore k equal to 1 and k equal to 2, just start from k equal to 3 in the recursive relation, then you can go ahead and probably you can compute all the coefficients, and if you do that, you actually get a solution y2, which is c2 x power 3, but this is nothing but same as c1. So in the earlier case, when you included k equal to 1, 2, everything, then you did not get a solution. If you ignore these two, just start with let's start from k equal to 3, you do get a solution, but that solution is same as the solution that you have already obtained corresponding to the bigger root. So you are not getting any new information, right? So the R2 is not really giving, so this the smaller root is not giving you a linearly independent solution as such. So now let's do what we already know, that once I know a solution, how do you find a linearly independent solution corresponding to the given solution? The reduction order technique, which we have introduced before. So let's do that, right? So what we are doing is we are looking for a y2 solution of this form, where this is your y1. Right? So if you use, then you apply the technique that we have already introduced before. So we need to solve for v. So if we use it in the ODE, so if you use y2 in the ODE and all that we did before, then you get an ODE for v. If you solve for v in this ODE, you get v to be integral of integral of e power x over x cube. Right? Now use this information in y2 here, right? So you have y2 of x equal to x cube e power x integral x minus 3 e power x dx. Right? This is your y2. But let's try to write it in the series form. So to do that, what you do, you expand this e power x in the power series form. Rest everything is same, right? So y2 is this times v, this times this is your v, and in v you have expanded e power x. So here again what I have done, I have expanded e power minus x, and if I multiply x cubed to e power minus x, I get this. And here if I multiply this inside and if I integrate term by term, so x power minus 3 on integration will give you this. Similarly, x power minus 2 on integration will give you this, and so on, right? So this is now this is just product of two series. You know how to do product of two series. If you use the product of two series, you get this. What we have done here, I have just segregated this term here, and this is precisely this term, right? This is what I expanded here. So this term and this term, I have brought it out here. Rest of the terms are here. So the reason I have written it like this is to show you in the form that we had it in the theorem. So your second solution is now coming as some series plus constant times the y1 times log x. Okay, so the general solution is a linear combination of the y1 that you had before and this y2. Okay, so that is how we have solved for the we have found the second, the other linearly independent solution corresponding to the y1. Okay, now let's do the third case. Okay, and for that we will use this this very special equation called the Bessel's equation. So a Bessel's equation of order p is an ODE of this form. Okay, so it's x square y double prime x y prime x square minus p square. So this p is fixed, which is a real number. P is given. So whatever the p is here, that is the order of the Bessel's equation. So this is called a Bessel's equation of order p. Okay. Now what is a Bessel's equation of zero order? That is, this is 0. P is 0, which means you have x square y, x square x. So if your x is non-zero, because if you are depending on your domain, if you divide it through, this is your Bessel's equation of order 0. Okay. Now let's find the solution of this ODE, which is a Bessel's equation of 0 order. So here if you notice, 0 is a regular singular point of the Bessel's equation. We look for a solution of this form with C0 not equal to 0 like before. Okay. So if you differentiate this twice and plug it in this ODE, right, accumulate like powers, similar powers, then you get this relation. Okay, you get this relation. So equate everything to 0 here, all like powers both sides to 0, then you get the indicial equation and everything, which is r square equal to 0, which is coming from this because C0 is non-zero. Then you have this equal to 0, right, and then you have a recursive relation coming from here, which is this. Okay, so in this case, if you notice, your r is 0. So you have two roots and both the roots are same, which is actually 0, which is r1 minus r2 is 0, right? Okay, so if you use r equal to 0, so you get these roots r equal to 0, and if you use r equal to 0, you will get C1 is equal to 0 from here, you see. So r is equal to 0 from this equation, and once you put r equal to 0, what you get is C1 equal to 0, so you get C1 equal to 0, and then you put r equal to 0, you get here, if you put r equal to 0, you get this relation. Since C1 is 0, all the odd indices are 0, all the coefficients with odd indices are 0, and then you have C0 already, and so all the coefficients with even index depend on C0, right? So you have C1 equal to 0, you have this relation CK, which means you have this solution Y1, which is the one Frobenius solution for the Bessel's equation of 0 order. Okay. Now, what is the other solution? So you need to find a linearly independent solution, right? So just a definition at this stage here. So this is a very special class. So as you see, it is actually a polynomial here, right? So this is actually a very special class of function which is called the Bessel's function of first kind of order 0, and it's denoted by J0. This equation, when you put C0 equal to 1, whatever you have here, this is a Bessel's function of first kind of 0 order, right? Because the equation that we started with is 0 order equation, so it's this is y1 that you obtained here is the Bessel's function of first kind, and the special notation for this function is J0. Now you need to find the linearly independent function corresponding to this y1, right? And that you can do by using the reduction order technique. You start with a y2 with the assumption that y2 is v times j0, right? And like the reduction order. So this theorem 97 is the reduction order technique that we introduced, and that gives you the formula for this v. That v is integral of 1 over x j0 square. Please do it. Use the reduction order technique, right? So basically take the y2, substitute in the ODE, right? Then you have an ODE for v, solve for the v, then you get what is v, and that gives you y2 is this, okay? And this y2 will be linearly independent from this y1, okay? And that is what will give you the general solution for this equation. So this is the third case that we have done. So with this, we have completed this lecture. So as I said in the beginning of the lecture, this is a lecture covering 2 lectures, okay? So you can see it in 2 parts. You don't have to hurry through everything. So I just did not divide it into 2 parts so that the entire material is there together in one lecture so that you can see it all together. Okay, then see you in the next lecture.